I call the Kirkwood-Batchelor formula. It tells you how to relate average fluid properties for Newtonian solvent to the stresses and conformations of particles that are immersed in that solvent. And that's really very fundamental. So now, and so then on Thursday then, I'm going to give a talk about flapping in various contexts, flapping of wings, flapping of flags, both experiments and modeling and their relation to load motion. So I'll get back to it on Thursday, the last, kind of close out. I guess I'll recap at least the part of the summer school I've seen. Okay, so, well, let me, okay. So what I'm going to talk about, and actually it's easier if I go to the next one. So I'm going to talk a bit about modeling these kinds of systems. In fact, there's, I think, a couple of the people who work with me who are here, tomorrow and Kayla, are giving short talks this week on some of this work as well. And so I'm going to, like I said, spend maybe the first 45 minutes outlining how you would, one very simple model of the fluid that's up above here. And so let me just kind of walk you through these various examples. Okay? So these are from a set of experiments by Victor Steinberg and his collaborators looking at the transport properties of viscoelastic fluids, namely just dilute polymer suspensions. And so in this particular experiment, we just have a little tank of polymer suspension. I think it's about 2 or 3 centimeters across. Okay, and it's being forced in a very simple way. And so what you're doing is you're looking down or from the bottom or something like that. But what you're doing is you're looking. Oh, it's actually upside down. Okay, that's nice. So this little tank, the bottom plate is being rotated. Okay, so it's being put under kind of a shear. It's a very simple shearing. And it's being rotated very slowly. And so what that means then, of course, is that the inertial effects of the fluid are small. In this case, I think they're around 0.1. And in other experiments, they're actually quite a bit smaller than that. But just think of this inertia, the Reynolds number, being out of the game. Okay? So now you're just dealing with something that looks like a Stokes equation, but it has a forcing that comes from the fact that it has these polymer coils that are immersed in the solvent. And these polymer coils have very interesting effects on the fluid. They give you viscoelasticity. But it's not just that you get a kind of elastic response to forcing. It brings in nonlinearity in a very big way. In fact, it brings in transport nonlinearities into the models, at least, that are lost when you throw away the inertial terms in the Navier-Stokes part of the equations, right? Because there you had del U del T plus U dot grad U. Of course, that U dot grad U, that convective nonlinearity, is the thing that gives rise to all sorts of interesting things like turbulence, which I think guys learned everything about 2 weeks ago. Okay, but those kinds of terms get reintroduced into the game by the presence of the polymer stresses. They have transport nonlinearities of a very peculiar form, and I'll talk about that.
But Mike, the black dot is just a...
Oh, yeah. Yeah, what is it? The eye of God. So what you're seeing here is just a little drop of dye that's been injected into this. And so if this were just a Newtonian fluid, well, you all saw Taylor's, video, right? I mean, so long as you're on a kind of a convective time scale, and you've thrown away convection, diffusion is very, very slow. And you're rotating this, that dot will just stay there in the center. But because of the instabilities that's induced by the nonlinearities of the polymer stress field, this starts to mix and form vortices and things like that that are in some ways very reminiscent of higher Reynolds number flows. Okay, so if we were talking about Navier-Stokes, we'd be talking about Reynolds number. dE dt is equal to minus grad T plus Laplacian U. In fact, I shouldn't do it that way. You do it this way, that's better. Okay, so we're talking about a high Reynolds number flow, where this term becomes rather small, except in your boundaries. And then if you're talking about a viscoelastic flow, back to, say, one that is low volume concentration, so like a dilute suspension, then you're dealing with something that looks like this. Where I have a Stokes equation, where if this were just 0, right, I had no polymers, that's the extra particle stress, then this dot would just stay where it was at. But this is the stress that's induced by the presence of the polymers in the fluid. And this has a peculiar transport associated with it, which involves a convective derivative, but also other things. And that's what I'll talk about. So here there's nonlinear transport. Rotation and stretching. I just want to push this analogy a little bit further, okay, because it's going to come up in a bit. So, if I take the Navier-Stokes equations again, and let's kind of formally take the limit Reynolds number going to infinity, so I'm not dealing with what's going on at boundaries and boundary layers, okay? Then I simply have udt is minus grad p. If I take a curl of this equation, then what I end up with is, and of course, the vorticity is curl across u. Okay, so I take the curl now of the Euler equations. Then I have d omega dt is the gradient of u, that matrix, grad u, acting on omega. Okay? So you remember this, of course, from your week of turbulence. Somebody had to talk about vortex stretching in the Euler equations, right? I spent the early part of my life dealing with this equation for years. I was looking at singularities in the Euler equations, Navier-Stokes, all this kind of thing, writing big, spectral codes with adaptive meshes. Thank God I'm not doing that anymore. But I know a lot about this equation.
Some people like it.
So, what's that?
Some people like it.
Yeah, well, so do I. It's very pretty. So the thing to say, though, is an important point, is that everything in the Euler equations is about geometry. It's all about geometry. It's about the geometry of the vorticity field. That it tells you everything about the flow, through the Biot-Savart law, rewritten in the Lagrangian frame, this kind of thing. So Euler is all geometry of vorticity lines. It's actually very much the same here in these viscoelastic flow models. It's all about geometry. And that's actually what makes them very pretty. Well, let me just set something on the board so I won't have to come back to it later, since I have Navier-Stokes up on here now. I wonder if I can displace this projector a little bit. There we go. If I look at the tensor, let's call it M, which is omega transpose. Okay? This is in the context of magnetofluid dynamics, where this omega would be the magnetic field. This is something that would be called the Maxwell stress. Okay, but let's just say I take a look at that tensor, omega transpose. And I look at its transport. So I look at ddt of M. Well, that's ddt of omega transpose, which is d omega dt omega, thank you, plus omega d omega transpose dt. This is equal to grad u omega transpose plus omega transpose grad u transpose. Right? And what's omega transpose? That's M again. So this equation closes for this rank 1 tensor M for its evolution. So I can rewrite this as dm dt minus grad U big M plus M grad U transpose. Of course, I didn't put a transpose here because M is symmetric. Is equal to 0. This is what's called the upperconvective derivative. This is a particular kind of transport operator on fields that are constructed from rank 1 tensors that have stretching equations. Okay? So if I have a dynamics, and this is going to come up in these polymer fields, because what's going to happen is you're going to model a polymer coil as some sort of linear spring which is being stretched by the fluid. Just like vorticity gets stretched by the fluid. So you're going to have a piece of that dynamics that looks like vorticity stretching. And then when you form a tensor, actually by some sort of distributional average of rank 1 tensors, you're going to get this kind of transport operator. But it shows up kind of generically anytime you're talking about transport of a tensor that comes from rank 1 fields, where each of the pieces in that rank 1 tensor comes from stretching. Okay, so this thing we will write as M upper triangle. Okay, so this is called the upperconvective. Okay. See, this is a little free form. I forgot where I started this from. But it's just good to, it's going to be good to see this. Okay, so you can see what I'm saying is that in this polymer stress piece, this term's going to have this upperconvective derivative as part of its dynamics. So there's stretching nonlinearities that underlie it, and that's an important part, it's thought, in producing the kind of unstable dynamics that you see, even at low Reynolds number, because you have the nonlinearity of stretching in the polymer flows. Okay. So I'll talk about models for this. And these are actually another set of complementary experiments that Steinberg and his friends published a couple of years later. And what you're seeing here is a microfluidic channel, which is a bunch of wavy turns like this. It's kind of a pipe flow in a wavy geometry. Okay? There's about 30 in this particular experiment of these little loops. And the channel width is around 200 microns. So it's a microfluidic flow device. And but it's the same kind of experiment. What they're doing is they're pumping in a dilute polymer suspension through 2 pipes, both at the same constant flux. One is dying and one is not. Now, if that were a Newtonian fluid in there, these dye streams would remain separate. But what happens is, as it flows down the device, this is just showing you a different station. So actually there's like 60 of these loops. That's the 30th station. Oh, no, let's see. Oh, pure solvent. Good. Okay, so that's the 30th station of pure solvent. Okay, so here is with the dilute polymer suspension. There's the mixing that occurs after 8 loops, 30 loops, 60 loops. The fluid just gets homogenized because of instabilities that are taking place inside of this channel.
Mike?
Yeah.
So how would, for a low Reynolds number, if you rotate one direction and you rotate the opposite direction?
These are irreversible flows.
These are irreversible?
Yeah.
Okay.
And that'll be easy to see from the models because there's a relaxation time. If you have a relaxation time in your model, it's not going to be reversible.
You mean from the polymer nature?
Yeah, so it comes from polymer relaxation to distinction. Yeah. Okay. Now, in part what Lisa's going to talk about is this problem, among other things. And this is the swimming of a spermatozoa through a viscoelastic fluid, which somebody asked about last week, about swimming in viscoelastic fluids. And so we've done some work on that problem of whether a viscoelastic fluid is an aid or a hindrance to the locomotion of an undulator. And it turns out to be a rather complicated and interesting question. And Lisa will talk about that a bit in the context of the Oldroyd-B equations, which is what I'm going to hopefully get around to deriving today. And I won't talk about this because tomorrow we'll talk about this. This is what you would call a problem with an active pulling fluid. It has to do with microtubules being pulled on the proteins in the cytoplasm. another kind of complex fluid. But then in the latter part of my presentation today, I'll talk about this problem, which has to do with the derivation and properties of the hydrodynamics of an active suspension. Okay? So instead of thinking about having a bunch of polymer coils that are immersed in a Newtonian solvent, I'll think about having rod-like swimmers that are propelling themselves through the solvent and producing stresses by their propulsion, and how that all couples together as a big hydrodynamic complex fluid. And so it's a companion piece to, if you like, to the talk that Joni gave last week on active gels. So there are instabilities again, but there are different instabilities than those that are associated with active gel instabilities, which are more Friedrichs types associated with liquid crystal elasticity. Here we won't have anything like elasticity, and there's a flow instability that comes from the active stress, but it's just of a different source. Okay. Okay, so there's more of this kind of thing. Yes, sir.
I have a quick question about the mixing that you have up there. So if it were just if I understand, is the flow direction this way or?
Gravity is irrelevant.
Okay, but
to this problem.
for those pictures, the flow is up and down?
It doesn't, I mean, just imagine, it's probably right at the top of this loop or something like that, where you're going to have a curved streamline.
Okay, so I guess what I'm wondering is, if it's just a Newtonian fluid, I would expect some kind of just broadening due to Taylor dispersion.
That's right, but on this time scale, you don't see it.
So here it seems that for the polymeric case, it's actually pulling out into lines. It's not just a broadening of the interface, but it's actually these lines that are flowing. Is there any reason for that?
That is not well understood yet.
Okay.
So there is now some modeling work by Alexander Morozov looking at 2D flow in a channel. What's thought to be implicated here are what are called hoop stresses. Right? And so in these parts where you have curved streamlines, you're stretching out the polymer coils along streamlines, and they exert kind of a hoop stress on the fluid and stop the moves of gravity instabilities. Is that how they translate themselves into particular flow structures? Theoretically, that's not understood. It's very difficult actually to visualize. People have been trying to do some stress visualization, actually, using birefringence and these kinds of things. But this is pretty much in play. Now, I'll do a little bit of mathematics now. Okay, Quorum? Yep. Wouldn't mind helping me here. Thanks. So I was an undergrad here at Boulder. And I realized this is the first time I've ever used a board at my institution. And it also reminds me that I had this calculus professor named, I'm sure he's long retired, Al Lundell. And he was an excellent teacher, but he was very methodical. So, that's pretty methodical, right? But the way he would erase a board is he would stand here like this. Really? Like the first few minutes of class, he just marches back and forth. It's just completely maddening. Right. Okay, so let me talk about Bachelor Kirkwood. I should really call it Kirkwood Bachelor. Let's be correct. I always call this the Kirkwood Bachelor formula. I'm sure many of you have heard of the Kirkwood formula, which is used to calculate what is the extra stress induced in some sort of continuum medium by the presence of some kind of what you would call non-hydrodynamic stresses. And I'm going to talk about that type of formula in the particular case of having particles that are immersed in a Newtonian solvent. Okay? No one did this, right? No. All right. How many of you have seen Kirkwood theory? Yeah, okay. Some of you. Okay, so here's the game. What I want to do is I imagine I have a volume of fluid, and again I'm going to assume that the inertial forces are negligible, so I'm just going to be dealing with the solvent forces, or rather the solvent stresses in Newtonian fluid, is it reacts to the presence of particles that are immersed in it and exerting stress. Okay? So just imagine I have a box. It's full of microscopic particles. They have some conformation. There's some concentration. It may depend on space. They may be rod-like particles, so they're going to have an orientation. They have a position. Maybe they have a volume, things like this, some set of conformation variables. And what I want to do is I want to have a way of calculating what is the average stress that those particles create in the surrounding fluid, so that I can derive equations for how an appropriately averaged velocity field evolves or is produced in response to those particles. Okay? So this is just kind of a sketch of that. So here's my volume. Now, I got up at 5 this morning to write these notes. So my sign conventions may not be conventions, they may just be errors. Things are your normals pointing in or out, all this kind of thing. So everything is correct modulo a sign error here or there. Okay, but here's my fluid volume, we'll call it V. And it's got some length scale, big L. And it's filled with particles. Okay, so volume V filled with many numbers n, much bigger than 1. So, if we're talking about something like a polymer suspension, we've got to have Avogadro's number in our back pocket so we can have a lot of particles. That exert a surface stress. So they all have surfaces on the surrounding Newtonian solvent. So that means Newtonian, that means that I have, I'll call it the fluid phase. I have a stress tensor for the fluid phase. Which is just a pressure piece plus mu grad U plus grad U transpose. There's my Newtonian stress tensor. Okay. And it satisfies div dot sigma F is equal to 0, which is the same as minus grad P plus mu velocity mu, and it's incompressible. So those are my solvent equations. Okay. So now what I'm going to do is I want to get an equation for an average stress, not over the whole box. That's maybe not very useful, because maybe I'm forcing the system somehow. Maybe fluid's being pumped through it, the suspension's being pumped through it, and I have a wall here, and so I have some sort of, stress, or rather some shear. And maybe there's inhomogeneities in the flow that I want to capture. I want to capture the evolution, like that fine scale structure in the polymer distribution that you saw in those images from Steinberg and Grice. Okay, so there we go. So now what I want to do is I want to find another box. I'm going to parcellate, divide up this big box into a bunch of small boxes. Okay, so parcellate big V. That means I'm going to cover the whole thing, but with overlaps, as I'll show you, into subvolumes. And here, this is going to be omega of x. So what I mean by omega of x is I'm going to take a point in the fluid, and I'm going to build a box around it. Where right in the center is a point x. And this box has scale L, little l, in every direction. Okay? And I'm going to choose these little boxes under the assumption that L is small enough that the gradient of the velocity, whatever that is uniform over that box. Okay, so there's some large scale flow, and it has a length scale, call it big L if you want. Now I'm going to take a sub box over which I can assume that that flow has constant gradient. It will change as I move along, but I approximate it constantly over a small volume. So it's small enough for that, but large enough that it will contain many particles itself. Okay? So I parcellated this into subvolumes, so I'll write this as x plus or minus L over 2 cross y plus or minus L over 2. So it's just an x-centered box. Okay? Where grad u is a constant over omega of x for any x that I choose, and omega of x has many particles. I'm gonna write these notes up. This is the one thing that's an addendum to the notes that we have in hand. Okay, I just state a result. I don't give the derivation. It's kind of nice to see the derivation. You get to see where you make assumptions along the way. Now, let me just say one thing I want to say about these particles. I want to say that these particles are force-free. There's no external body force that's acting on a density difference, anything like this. It's a force-free particle. Okay. So, now what do you think I'm going to use this omega of x for? Why have I done this? Yes?
Lagrange.
No. I'm going to use that as a volume over which I average. So I'm going to write down equations for quantities that are averaged over those boxes. They're still a function of x, so I'd let x be the center, but I'm going to average around it over this box. I'm going to get effective averaged equations. Okay, so here's my particle. There it is. I'll call this particle d sub I, that's its volume. It's going to have surface delta d sub I. And what's it doing is it's exerting a stress on the fluid around it. It has some surface velocity, v sub I, that's the ith particle. And it's got some outward normal, ni.
How does the volume, this omega, compare to the core training volume compared to the size of the particle?
We're going to assume that the volume of the particles take up is small relative to the size. It's a Duluth theory. So we're going to assume that the particle volume is small relative to this volume I'm averaging over. You'll see it show up. You'll use it very strongly, actually. I'm going to keep volumes floating around in this thing. And you'll see where it shows up. Oh, okay. Force-free. They exert no net force on the fluid. So this means if I look at the surface integral over any one of my bodies of g sub I, that is 0. Okay. Usually now this is a typical low Reynolds number flow assumption for when you have a free body in the fluid. It exerts no net force or torque on the fluid. And that's because the inertial forces in the fluid are negligible. And if you're nearly density matched with the particle to the fluid, then the inertial forces that are associated with the particle are also negligible because they look like Reynolds number times the ratio of masses of the mass of the fluid to the displaced density. So usually end up turning Newton's second law into something that looks like this. A little Reynolds number. Okay, so that's force-free. We'll also assume there's no net flux of mass. So ds vi dot n I is 0. Okay, it's going to be no net flux. Could be impermeable. And now to make the calculations easy, and that's because it's the only way I know how to do it right now, this is the way Bachelor does it. is that we're going to assume that the interior mechanics of the body is also associated with the stress tensor that has zero divergence. Okay? So let's assume internal mechanics governed by sigma super p, so I have a sigma super f, okay? Where div dot sigma p inside of each body is 0. Okay? So maybe it's some sort of elastic solid with negligible inertia, something like this. We're really going to use it as an intervening device to express things in terms of surface quantities, in terms of this G.
So what's the difference between G and sigma P?
Well, that's this, boundary conditions. So, one is no slip. So, V sub I is U evaluated on the boundary. And the second is continuity of stress. So what that means is that the surface stress of the fluid is exerting the sigma F. That's equal to the particle stress. And by a sign convention on the normal, that's equal to minus G. Okay? So G is a surface stress. In this case, it's given by the internal stress tensor or the fluid stress tensor under a continuity condition. Okay. Now we're going to, so I'm going to have some total stress. Sigma, which is going to be, I have an indicator function. For a fluid region. I'll call this omega F of X. That's just in this volume here. It's the part that's taken up by the fluid, external to the particles. So I have chi sigma F plus 1 minus chi sigma P. So I'm inside of the particle, then chi is 0. Okay, and then I just end up having the particle stress. So it's just a jump function. Okay. That's an F, and then I'm also going to have a sigma P for the particle domain. Okay, now I'm going, after all this preamble, now I'm going to just define what I mean by an average stress. And then I'm going to give you a bunch of exercises. Okay, so let's define sigma bar X to be 1 over the volume. This is just the volume of omega of X, so total volume. 1 over that volume, integral over omega of X, dVy sigma of Y. So that's just a sum of a couple of integrals using the indicator function over these respective domains, using either the fluid or the particle stress. So now, this is the stress tensor I'm dealing with. This is the stress tensor that I want to understand. Okay? That's it. It's the average stress. And it's a function of X, because I have this moving average volume that I'm moving across to form an average, a moving average, and I can take derivatives with respect to the center of the box. Right? So I can talk about, like, what is div dot sigma bar? What is the average Newtonian stress tensor over my box? Things like this. Okay? And so it all comes down to doing calculations, really just using the divergence theorem and my various boundary conditions and the fact that things are force-free and flux-free and stuff like that. Okay? So there's my average quantity. Here's your first little exercise. Show div dot sigma bar is equal to 0. Show that. Okay? And let me just say that to show that, you're going to need, well, okay, if you show it, it's only going to be true for force-free particles. Okay, so show that's true. 2, the only place I'm really talking about a velocity field in this whole thing is in the fluid region. The only thing that I'm going to use in terms of the internal particle stuff is the fact that it has a stress tensor, and somehow, of course, that's going to produce an acceleration or velocity somewhere in it, or a displacement. And I'm just going to talk about an average fluid velocity, not an average bulk velocity. So I need to define the average fluid velocity in terms of the fluid domain. So let's show that. My second comment is pressure and velocity are only defined in the fluid region. Okay, so I'm going to define then a U bar, which is 1 over the volume of the fluid region, okay? An integral over the fluid region, dVy. In fact, let me write this as U bar P bar, so I don't have to write something twice. U P, where those are my Newtonian velocities and stresses. So show div dot U bar is equal to 0. Show that. So again, so what I'm claiming is that under this averaging, I have a 0 divergence average stress. Under an appropriate definition of what I mean by average fluid quantity, I have a divergence-free velocity field. Now, let me make life easy for you. You might worry about what happens when this boundary moving around is cutting through particles. Okay, then what I'm writing down is not exactly right. There are errors. Have to do with some scaling of the particle size. Assume, just for the purpose of calculation here, to make it easy, that you're dealing with a volume that is not cutting through particles. Okay, they're in the interior, the exterior, but not cutting through. After you do that, think about how you get corrections to this. Okay, so show that. So in the case of cutting through particles, these are approximately true statements. So I have a divergence-free stress, I have a divergence-free average velocity field. Let's calculate the average Newtonian stress tensor. Now, of course, here we're averaging over the fluid domain again, because I'm talking about the solvent stress. Now, plainly, I have an integral over omega f of x ddy sigma f. Well, that's just omega f of x ddy minus p identity plus 2 plus mu grad u plus grad u transpose, which, by my definition of the fluid volume average, this is Vf times minus P bar identity plus mu, and this is grad U average plus grad U transpose average. Okay, that's just a definition there, nothing there. But, show the following. This is equal to Vf. Now, what's the thing here? This is fine, right? Just the average pressure over some subvolume. But now I'm averaging gradients. And if I want to have something that looks like a Stokes equation in kind of my long variables and my average variables, then I don't want the average of grad U. I want something that looks like grad U average. So I'm inverting, I'm looking at the Stokes equations in the outer variables. Okay? But the halfway step to this is that this is VF minus P bar identity. Minus mu, and then I have, oh, let's put that there, fine, minus mu integral, the integral over delta omega of x of u n transpose plus n u transpose. That's finally some divergence theorem thing, right? So here now, this is again a rank 1 tensor that's composed as an outer product of two vectors, okay? And then I have another piece that's over the particle boundaries, which I'll just write as the set delta omega p. That's the union over all the particle boundaries that are inside of my box. Same kind of thing. Okay? So you get that. And that's just a divergence theorem argument. Now, this I like. I'm expressing the average Newtonian stress in terms of some average field here, that's fine, it's just the pressure. And then something that involves surface quantities of the particle data, right here. That's over all the surfaces. That has to do with my definition of what an average was. I don't like this. Right? I don't want to have this floating around. It's an artifact of some sort. And it's an artifact that comes up because what I have in here are the average of gradients, grad U averaged. Okay? So what I want to do is I want to calculate instead, let's calculate grad U bar. Okay, so you get to calculate grad U bar. And so if you look at grad integral omega f of x of dvy sigma f, or uf, sorry, u, okay, it turns out to be equal to minus the integral del omega of x. This is turns out that you don't pick up the particle stuff. So you're just kind of shifting the outer boundaries, so those pieces in the average cancel out. They don't come in. ds u n transpose. So it turns out that this piece, which is the boundary piece here, that I don't like, so it has to do with the specifics of how I'm choosing to do the average, can be re-expressed as the gradient of an average quantity. That's nice. I can get rid of it by talking about the gradient of an average quantity, which is what I like. And so what you can get, then, in the end, is the integral over omega f dvy sigma f of y turns out to be df times minus p bar identity plus mu grad u bar, not bar grad u bar plus grad u bar transpose plus a boundary term minus mu integral over omega p of x and the integral over all those boundaries u n transpose plus n u transpose. Okay, that's nice. I don't have any surface integrals that are involved in the way that I'm actually choosing to do my averaging. All I have are these things that involve average quantities, velocity and pressure, and surface quantities over the particles that are in the volume. So, then I have one last piece. It has to do with the contribution of the particles to the overall stress.
Like your last integral was over what, the value of the particles?
Yeah, so omega p, thank you. Omega p of x is the union over all particle surfaces.
So it's over it's the
Right.
surfaces.
Right, so this is a sum of surface integrals. That's what that means. Right, so this is an integral of that surface quantity over every particle. You're adding them all up because integrals of unions are sums of integrals. Does that make sense? Okay. Okay, so this is what I like to call the bachelor trick. Well, it's sure older than George, now long dead. But here's the thing to show the integral of the polymer contribution ddy sigma ijp. Okay? This is equal to integral over the particle surfaces. So again, that's that union of surfaces, all these particles in there. dsy, oh, let me get rid of the operator. It's that gy transpose. Okay? So it's this sum of integrals of rank 1 tensors. You can see in here, rank 1 tensors are showing up everywhere. To show that. So what we end up with then is the following. Div dot sigma bar is equal to 0. Div dot u bar is equal to 0. Sigma bar is Vf over V minus P bar identity plus mu grad U bar plus grad U bar transpose plus 1 over V integral over delta omega of P dsy gy transpose, that's a piece, that's the stress really is coming from the particles, plus this extra piece. And this is the, what year was this paper, bachelor's practical, do you remember?
I'm good. Oh, I don't know.
1983 or something like that. The rheology of force-free suspensions, something it's called something like that, it's in GFM. But I end up with this set of now what would be forced Stokes equations, where I'm solving for the average pressure and the average velocity, and the forcing is from the so-called extra stress, the extra particle stress. And this is the basis for a lot of classical non-Newtonian fluid mechanics. So if you're talking about simple suspension theories for viscoelastic fluids, if you're talking about what's called Dewey rod theory, so the dynamics of what are called passive rod suspensions, or the dynamics of liquid crystal polymers. This is the kind of thing that is often started with. Now, I've got about 45 minutes left. So my point with this is that now I can write this. I can absorb, notice I have this ratio of the fluid volume to the entire volume. If I have a dilute suspension, this is always very close to 1. It can also just be reabsorbed into a definition of pressure and viscosity. Okay. So then I'm going to have something that looks like this. minus grad P bar plus mu Gaussian P bar is equal to minus sigma P bar. And often that's called the extra stress, and that's this piece right here. Oh, I did divergence on it. Okay. Now, let me just kind of sketch through a couple of the standard examples. And again, I only have an hour and a half on all this. I've already chewed up over half my time. And I'll show you some results of various sorts. So here's an example. So what's the game? I have a set of particles. I'm going to model them somehow. And I'm going to, yes?
I'm a little bit confused about how the microscopic assumptions show up in the final equation. Because basically the only thing that you allow is momentum transport, which is instantaneous through your particle volume, right?
That's because it's
So you have some
Stokes.
discontinuities
That's
in the
because it's
momentum
Stokes. Yeah.
transport.
It's all because it's Stokes.
Okay.
Everything is instantaneously balanced. There's no momentum in the problem at all.
Okay.
Okay, so, and here, I mean, there's also errors in this that I've suppressed by not talking about what really happens when the averaging surface is passing through particles. So I've written it down as an identity, but really it's an approximation. Okay, and those errors are going to be smaller, of course, the fewer, the more dilute your suspension is. Okay, so here's the classic example. It's called the dumbbell model. And it's a very crude model for the stresses that get developed by a polymer coil under distension. Okay? So, I have some polymer chain. It's in some sort of random walk configuration. It's in the fluid. It's been kind of entropically compressed by collisions with the solvent. And typically, this is just modeled as the dynamics of the so-called end-to-end displacement vector. So you take the ends of the polymer coil, or R is equal to x1 minus x2. It's got some center of mass. Okay? Now I'm just going to treat this as some effective model where the drag that's induced on the polymer coil is just associated with the drag on two spheres that are connected by a spring, just usually a Hookean spring. Not always, but usually. So I have some effective spheres that I use to drag this polymer coil out. And then there's the entropic force, of course, is trying to bring it back. So the picture is this. Two spheres, and in this, you usually assume that they're hydrodynamically uncoupled. So the only way in which they're coupled is through this spring force in between. It's a very rough model. So here's R. It's x1 minus x2. I have some center of mass at C, which say we'll just set at the center of the spring. And then I have a spring force. So here's my spring. And there's some spring force here, F of R. It's just usually taken as a linear Hookean spring. Okay. So, linear Hookean. That gives the old way B model. Then we have various other types of nonlinear models, like the so-called Feeney models, finite extension nonlinear elastic springs, where you assume that your spring law has a divergence at the particle, or rather at the polymer length. Right? Real polymers have finite length, they have a finite number of monomers. And so when you stretch them out far enough, you develop a greater force resisting extension. Okay? So Feeney are nonlinear models. These models do not close. You can write down kinetic theories for them, but they do not close at the macroscopic level. I'll show you what I mean by that. Oldroyd B closes at the macroscopic level. You can get rid of, we'll write down some Fokker-Planck equation, and you can eliminate the distribution function out of the whole thing. So, and that's all because of this linear assumption, which is its strength and its weakness. Because real polymers cannot stretch without limit. So that leads to various types of diversities in Oldroyd B. Okay, so we're just going to use Stokes drag law on two spheres connected by a spring. Stokes drag. So these are going to have some called radius A. Okay. And so I have 6 pi UA times, so I'm just going to assume I'm moving against some background flow velocity. I just have a Stokes drag acting on me. x1 dot minus u of x1. That's the drag force, and balanced by the spring force, which is minus kr. Okay? I have an equal and opposite force acting on the other sphere. It's a zero force-free, rather it's a force-free particle. So 6 pi UA, x2 dot minus u of x2 is minus k x2 minus x1. So, zero force. So this pair is kind of my particle. That's my effective particle that I would be using in my Kirkwood formula. It's this pair of spheres. So that's my particle pair. The conformation variables are its location and its distension vector r. That tells me how far apart they are, how much I've stretched that spring. So now, if I just take a difference of these two equations, I'll have r dot minus u of x1 minus u of x2 plus u of x2. Expand those velocities around the center point, because I'm assuming the gradient is constant over this whole thing. Okay, so I can just expand around there. So what this gives me is I'm just going to have that my center of mass moves with the velocity field, just kind of being propagated along, and that eta times r dot minus gram ur is minus kr. And that comes from doing this expansion. And here eta is just this 6 pi mu a divided by 2, which comes from having taken that difference and picked up a 2k. So 6 pi mu a over 2. Okay. So if you like, this is the evolution of my single particle conformation variables. Right? Now you can do another calculation. It says if you look at the volume average stress that comes from a single such particle, you would do the following. I have two spheres, each of which is being dragged by an equal and opposite force. Right? So you go back to Stokes's derivation and you find the surface stress for that. That's your G. You look at the integral of the surface stress times the position, you add them up for both spheres, and you make a calculation. So for a single particle, you're going to have this sigma p, the particle, or rather what we call sigma p, the extra stress, the volume average extra stress, is going to look like minus 1 over v my f of r times r transpose. Okay? That's the stress it communicates on average into my volume.
By single particle, you mean your pair of spheres.
My pair of spheres. My single particle is a force-free particle which is made up of two spheres connected by a spring. I'm really hungry. Lost myself. Okay. Yeah, I'm a really nervous person at the front. I mean, whenever I see videos of myself, actually, I think this is a real personality test. How many people like watching videos of themselves? I do. I don't know anybody else that does. So, My wife is really unimpressed by that fact. So now, so that's the kind of extra stress that this will produce. And of course, for this Hookean spring assumption, this is just 1 over V KRR transpose.
So your FR
That's my spring force. Here I've written F of R is minus KR. But generally, if I just had some distension vector displacement spring force, it would be sitting right there. So in the Feeney model, this would be some nonlinear thing that diverged when the modulus of R was the polar number. Okay, so now if I have m particles in my little volume, then I'm going to have sigma E of x is K over V, a sum over I, m particles, Ri transpose. Now, let me point something out. Back to the first part of my lecture. Sum of rank 1 tensors giving me a stress. Look at the dynamics of a single particle. R dot is grad U R. That's the same as the stretching equation in the Lagrangian frame for vorticity. Okay? So this is going to give me that upperconvective derivative. That's where that's going to come from. It's right here. And so now I can write this as minus n C of x, I'll define this in a second, 1 over m, sum over I up to m, minus k Ri transpose. This is total number density. I'm just introducing some variables, n over L cubed. Remember, I had a total of big N particles in my whole volume. So that's total number density. This C is a local concentration, because my m is a function of x. So this is equal to the number of particles per unit volume in my averaging volume divided by the total number density. So that is a fractional concentration, if you like. Okay, so I can write it this way. It's a local concentration times the averaged extra stress calculated over my particle conformations given by the distension vector. Right? And so I could write, and so typically what you'll do is you'll rewrite this as some distributional average, which is an integral. This is now passing to a limit where I have a large number of particles in my volume, so I can replace the discrete sums by distributional averages involving a distribution function. dvr psi of x r and t r transpose, where now this is my distribution function. So here this is passing to a distribution limit. Replacing the discrete sum with a continuous approximant. And now I'm going to evolve this continuous distribution function. This is the basis of kinetic theory. So this is going to satisfy a Fokker-Planck equation. And this psi is going to have some normalization. dvx dvr psi is 10 L cubed. You understand what I'm doing there?
Just don't write behind the cabinet.
What's that?
We cannot see it.
Oh, I'm sorry. I can't move this. Okay. So this I wrote as R transpose and average. We're now going to replace the discrete average by a continuous average involving a continuous distribution function. So this I'm going to replace by an integral dvr. So averaging over all my possible distension vectors, now with their conformation, their distribution properties described by a distribution function, and that's being averaged against the single particle stress, R transpose. Okay? So now moving to a continuum theory. I'm going to replace this with this distributional average. Now, the next statement is, I have my set of confirmation variables, I attach them to I take a set of particles, fixed set, and I track them through time. Their confirmation variables change continuously, though maybe I add diffusion fluctuation quantities to them as well to put in diffusions. But the total number that I have in any sort of volume that's being tracked in time is constant. That's a conservation of particle number statement. That gets turned into the Fokker-Planck equation. It's just conservation of particle number. Okay? So then, right, often it's just called conservation of probability, conservation of particle number. That gives me d sine dt plus div x dot. I'll write this as a flux. This is really now a function. It's not this x dot sitting over here. It's a flux function plus div r dot psi is 0. So that's what psi will satisfy. It's just a conservation equation. This is a Fokker-Planck equation.
What's x dot? What's x again?
Okay, let me write that down. And this is really what I'm doing now is I'm writing down the kinetic version of the Oldroyd V equations. So I have a Fokker-Planck equation. I have particle fluxes where I'm going to include into these flux functions the effect of things like center of mass diffusion or distension length diffusion that comes from thermodynamic fluctuations. So this will just be x dot is equal to u of x. Just writing down something that's going to produce a Laplacian for me. So it's a standard kind of diffusional flux. Of course, when you say standard, that's to keep you from asking a question about it, so I can move it quickly. Then I have r dot is grad u r minus k over eta times r. So that's the stretching, that's the spring force. And now I'm going to allow for the effect of diffusion on the distension vector. Okay. Now, it is the case that polymer coils are kind of big guys, okay? Diffusion constants associated with them are usually quite small relative to the effects of diffusion in kind of vibrating the distension. So this term is usually dropped, and this one is usually retained. Okay, so now I have the evolution of the distribution function. I've written down the fluxes. They come from my calculation of this dumbbell model, adding some fluctuations. But what I don't know is the velocity and the gradient of the velocity. So now I have to go back to my average Stokes equations. That's going to tell me what those are. Then I have where minus grad d plus u Laplacian u. So here, notice, I'm really assuming that I'm evolving my particles against the average velocity. So I'm not allowing for particle-particle interactions. And I'm assuming that the only way in which I produce gradients are by the actions of so to speak, faraway particles producing stress. So then this is equal to minus div dot sigma e, where sigma e is what I wrote down over here. That. I think I forgot a k. This is definitely, oh no, that's just the average of R transpose, and then I have a k when I actually have to form the stress. And I have this is equal to K div dot integral dv arm sine x rt r transverse. So this is kind of a very classical fluid kinetic model where I've coupled the kinetic description of the evolution of particle conformations to the background fluid that they produce by their movement.
No,
What?
it's not great.
Well, this is a DVR integral. So here, at each little volume, I'm averaging over all my possible conformations, all my R's.
There's no gradient. It's gay.
Sorry. God, right. Thank you. How embarrassing.
Just
Like I said, I'm maybe blood sugar. Okay, but now I have a closed set of equations at this point, right? I start off with initial data for psi. That tells me my local concentration and how the particles are oriented initially in terms of how they're distended, or whatever. How much stress have I stored initially into the polymer field? I use that to produce a stress here. That stress, I can solve the Stokes equations. I can get the velocity. I can get the gradient of the velocity. I need boundary conditions on these equations, obviously. I can form all my particle fluxes, and then I can evolve the distribution function. So that's the way it goes. Now, that's a nasty looking affair, right? You don't want to deal with this. You have, as a theory, as a hydrodynamic theory, if I'm trying to compute the evolution of this system, I have 6 independent spatial degrees of freedom. X, Y, Z, R1, R2, R3, plus time. You can't find a computer in the world that's going to do that for you. It's not good. But that's kinetic theory. That's what always happens. You exclude. So, but it turns out that in this particular case, because I made this linear Hookean spring assumption, I can write down a closed evolution equation with no R in it for this sigma E. I can eliminate the distribution function. And that's because it's a linear Hookean spring. If that alpha bar were nonlinear, as in theme, then you have to deal with this full kinetic theory, which people do under various types of closure assumptions, which are mostly less accurate than more accurate. Okay, so let me go back to this. So let me just say, here's another little homework problem, and it's just reproducing a calculation I give you in the notes. Write down the PDE for sigma E, which is K integral psi RR transpose DDR. Okay, so this is a function of x and t. Right? Write down the PDE and x and t for that quantity. To be able to write that in closed form means I closed the system. I've eliminated the microscopic variables. Thanks. And here's what you get. I should have way more time on this than I wanted to. There's my sigma, it's a solvent stress plus the particle stress. There's the solvent Newtonian stress. I have this equation. There's my thing I'm trying to model. There's my single particle fluxes, adding some diffusion terms. There's the extra stress, some constant times RR transpose. Okay? This is what you find. That there's again just the equation I wrote down here. I've written things in non-dimensional forms. Now you're seeing things like a beta, Heisenberg number, and stuff like this. Okay? So the variables are changing, but the form of the equations is the same. Here's this equation, momentum balance. There's momentum balance. I've added a background forcing for various reasons. And here is the evolution equation for the extra stress. And there's that upper convective derivative again. Okay? So I'm going to write this real big. Oh, wait, I can turn on the lights. So this is non-dimensional now. As the Oldroyd-B equations. Actually, what we like to call the Stokes Oldroyd-B equations. How many understand that joke? How many Americans are in the room? It's kind of the same question. Okay, so I have that right there, but here I have Weisenberg, so-called Weisenberg number. Times sigma p upper convective derivative is equal to minus sigma p minus the identity. Okay, and let me just say here, so I've set, as is customary, though I really don't want to do it, I've set the translational diffusion to 0. So here is that upper convective derivative we talked about at the beginning. And it arises because I have this thing constructed out of our R transpose things where, you know, these R's are being stretched by the background gradient field, just like vorticity stretching. This is a relaxation term. It's a time derivative against a relaxation term. Strange time derivative. Okay? And this term here is actually being produced, that minus the identity in non-dimensional form, is being produced by this fluctuating term in the distension vector, and it just says you create an isotropic stress just by vibrating these things, you know, these coils thermodynamically. It creates a stress, extra stress in the fluid all by itself, even in the absence of fluid. Okay, but the main thing is, this is nonlinear transport, rotation and stretching of a tensor. Okay, it's this sigma p tensor. That's what makes it look a lot like Euler, is this guy. I've written it as a tensor, rather for a tensor rather than for a vector. Okay, so that's Oldroyd-B. In this predicted Stokes Oldroyd-B, SOB equations, I have a coupling of the solvent dynamics to an extra stress which has a nonlinear transport equation. Okay, now this Weisenberg number is the ratio of the so-called polymer relaxation time. I distend this thing and it relaxes on some time scale, right? If that's at minus k over the damping k over lambda. To some forcing time scale. Say it's coming from boundary conditions, I'm shearing it, or I have a background flow in there somehow that's stirring everything up. The relative kind of non-dimensional relaxation time is this Weisenberg number. Okay? And then there's a beta. It's a non-dimensional coupling strength. How strongly does the polymer stress enter into momentum balance in a non-dimensional way? Okay. Well, let me just show you a few things that happen here. Now, these are just numerics. Let's say I take the Oldroyd-B equations, and I put a background forcing.
Can you get the lights on?
Yeah. Turn them off. Okay. Hip works either way. I'm going to put a background forcing on it, on an Oldroyd-B fluid, just in 2 dimensions. So here's a background forcing field, because I add an F into momentum balance, body force. And I use it to create kind of a so-called 4-roll mill geometry. So I'm going to be stretching polymer coils at this central stagnation point that you see. Stretching is very important, of course, in polymeric fluid mechanics, as it is in Euler flows and vorticity flows. And these are some of the kinds of things that you see in these types of flows in terms of the fluid response, because it has this polymer stress. you know, if there were no polymers in this, the flow would look just like the forcing like this. But because I have the polymer stress, it turns out you can go through a sequence of bifurcations where you go from being slave to your background forcing, because you're near Newtonian. You increase the Weisenberg number a bit, which means the fluid forcing is relatively more important. Then you can undergo a symmetry breaking, and then you can go into really kind of crazy multi-frequency behaviors out of this that lead to fluid mixing, actually. And so this is all low Reynolds number flow. And let me show you the movie. This is the vorticity field of Weisenberg equal to 10 when you're past some sort of critical bifurcation to oscillation. Come on, baby. This isn't Peppo's machine. I mean, it won't work.
Is it me?
Great, I've gotten it back. Let me show you another one instead. Oh, I hope I said name, but I may have been wrong. I just hit whatever the default is.
Yeah.
Yeah, okay. So here's a movie of such a flow. So first there's a rapid relaxation. You start off with just isotropic stress, then it rapidly relaxes and moves away from that. And what happens in this, at least qualitatively like what you see in the experiments, is you see the formation of very time-dependent vortical flows. So this is the vorticity. And what we find here is that we get a precessing vortex that just wanders around this 4-mole mill cycle forever and ever and ever. And that kind of structure really mixes fluids, homogenizes fluids nicely. It's like having a rotor that you turn on here, 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 here. And it just cycles around. It's kind of the natural, it's one set of intrinsic natural dynamics. And then over some longer time scale, it moves into what I call the washing machine mode. You know, when the machine starts doing this as it's kind of going around. And what you get out of that, and this is from a whole series of papers with Dr. Thomas's and more recently with Jean-Luc Tifo. And what you get is that this is what happens to a set of particles that were starting off with solid colors in each of the quadrants. That over a long time, so it makes them very homogeneous. So it's a nice mixing flow over a long time. Okay, we'll homogenize the fluid. And again, like in the experiments, if I had the polymer stress not in the problem, then this wouldn't happen at all. Okay?
What are
You just
you
have
plotting
slow
on?
molecular diffusion mixing things. I heard a question, yes.
What's there on the vertical axis? What are you plotting?
Oh, what's being shown here, find the row. Oh, yeah, now I remember. Okay. So, call this quadrant the blue quadrant. So initially, all the particles in here were colored blue. Blue, yellow, red, green. So the fraction of particles that were colored those other things in the blue quadrant, it equals 0 over 0. One for the other one. Now you're watching how they're all going to a quarter in time. Let's see if I can make this other one play. Now that I've enabled all my bad content. Okay, it's kind of irrelevant. So you can play other kinds of games where you increase the number of rollers in there, so you can think about having more spatial degrees of freedom and see how the whole system arranges itself, so that's kind of fun. You get a lot of non-stationarity, you get broad spectrum frequency content, lots of things that are kind of signals of having strongly mixing chaotic flows. And then we've been doing some experiments too. We reproduced some of that in experiments, and this is just, in our lab at Courant, an experiment using a 4-mole mill setup where I have discs sitting underneath the fluid layer to create a 4-mole mill, and this is looking at a PID image. What happens is you cross the symmetry breaking modification, for example, in a real fluid. So you tend to see these things. Okay, now, how much time do I have? I asked myself.
2 minutes.
I got 2 minutes. So, here's the deal. I have another talk on Thursday. I'm ready to go on, and if you guys like, I can find another hour sometime where I can talk about active particle suspensions, because we've already set the whole background for it. And all I need to do is to change the single particle fluxes, do another stress calculation, and we can talk about active suspensions for things like bacteria. So somewhere tomorrow, Wednesday, we'll find another hour, okay, if you guys want, just let me know. And we'll talk about active particle suspension theories. It's kind of a more biological, complex fluid. Okay.
Thursday there's one. Yeah, we have one.
Oh, yeah, that's right. I'll give 2 talks on
For
Thursday.
3 hours.
Yeah, I'll do it.
There is a lab visit on Thursday.
So, on Tuesday afternoon, after 4.
After 4 we have.
Yeah.
Okay. I mean, it's really easy at this point. I've done everything for you. Okay. Yes.
I have a quick question about just what you just presented. So, intuitively, should I think that if you have that floral mixing setup, but instead of having a polymeric fluid, you have, say, a fluid of just particles like rods or something, rigid rods, would you still expect some kind of intense mixing in that case?
That is an interesting question. You would expect something to happen there,
Yeah.
because you're going to have various types of alignments because of Jeffrey's equation. Actually, I'll talk about that tomorrow.
Okay.
Okay, it's going to be a special case of what I talk about.
I guess what I'm asking more generally is this, do you expect this mixing to happen in any case where you have...
Stagnation points are always interesting in complex fluids, because they tend to align particles, and then you change the rheological properties of the suspension. So another type of, so here, let me just, I'm T-1, so what happens in a place like this, right, is that you're stretching the particles there. You're stretching the polymers. You get a lot of polymer stress. Now, there's other, so to give you another example, imagine instead of having the stretchy particles, you have something like a flexible, semi-flexible polymer. You just have some sort of flexible rod that's in the flow. Okay? And it turns out, oh yeah, now I remember the point I'm starting to make. What's going on in a second? So if you take a look at the old D equations, where you have a background flow, and you look at kind of solutions in the neighborhood of stagnation points, then if the stress at the stagnation, or rather the strain rate at the stagnation point is small, then you'll kind of saturate to some constant value of stress that comes from stretching the molecules. You'll get a balance of the stretching to the spring force, and they'll equilibrate and be in balance, and they'll sit there. There's a critical value of the strain rate where you start to see divergence of the stresses exponentially. Namely, the straining flow is long enough that it cannot balance, or rather the storing spring force cannot balance the straining flow. And that's called the coil stretch transition. The coil stretch transition is very, very interesting. So nonlinear versions of the coil stretch transition were first looked at by DeGene and by Hinch in 1974. And what they showed is that this coil stretch transition was associated with hysteresis, bistability, and all sorts of interesting things in flows, theoretically. And that was shown by John Chu's group back in the 90s using fluorescently tagged DNA molecules as their kind of long chain polymers. So there's a set of bifurcations in here that actually, of these coil stretch transitions, that actually underlie the bifurcations like symmetry breaking and oscillations that we see in our simulations. The second point is if you take a different type of particle, you take something like a flexible rod rather than some sort of chain you're going to pull out, and it turns out that when you get yourself in the neighborhood of a stagnation point, so you have something like this, imagine I have a rod that's being transported down by the flow, but it's elastic. It gets turned, and then it starts getting stretched. Oh, I have it going the wrong way. What am I doing? This, oh yeah, here we are. I have to make a full stagnation cycle so I get it right. So imagine I have a rod coming down like that towards a stagnation point. You're asking about rods. I'm just going to make it flexible. Interesting things will happen to the rigid case. What happens to a rod at a stagnation point when it's lined up with a stable manifold? Mechanically, what's happening to it? It's getting compressed along its axis. There's axial stresses that are compressing it. That can drive a buckling instability. And so it turns out that there's another instability. I call it stretch coil transition, because you can go from having something which is stretched out as its native state to something where instead it's buckled. And that has very interesting dynamics too, as a complex fluid system. You can have random trafficking of direction because in talking you may end up going this way or that way. You develop compressive stresses that relax on some time scale. Again, there's kind of Weisenberg number that tells you how you'll restore stress back to the fluid. So stagnation points are always interesting. That's the main. That's why you look. Okay, other questions? Okay, thanks.